Amanhã, né? Ainda me fale banal, especialista. Lulesas. Ha. Aghajanyan çok güzel. Evet, hem yapmayayım. Ha. Wow, eşit. Evet. Mm. Mire cuando ninguém me casqué sin celular. Mucho avanzas con Google.
Hey guys, so we're starting the day. Uh, in the interest of time, we're going to go through the implementation, essentially line by line to understand what's happening, what you were working on yesterday, what you should have done, what you should have achieved, more or less. And yeah, enjoy the show.
All right, guys. I think for the sake of time, let's run quickly through the initial transformers implementation, and then I will give you guys the ground truth for the llama implementation offline. And then after this, I think what we'll do is we'll finish up the lectures from yesterday, and then we'll jump into multimodal. Uh, I think this should be fine, right? You guys can hear me? Okay, so maybe let's start off with probably the most complex part, which is the positional encoding. Um, the core idea, if you recall, is that you essentially want to set um, um, you want to give a rotation matrix to the underlying vectors or to the underlying embeddings. And the core idea is pretty simple. So essentially, what you do is you create a static vector where the even terms are sinusoidal and they follow some frequency. By default, I think people have picked 10,000, and we do the same here. Of course, normalized by the dimension of your model. And for all the odd elements, you have a cosine pattern with the same exact fixed frequency. And embedding is very simple. I mean, all you do is it's additive to the original embedding. So you just slice the positional embeddings for however long your current input is. And yeah, that's about it. And this is probably the most complex portion of this implementation. Multi-head attention, I think you could have followed exactly the formulas that were in the slides. So here you have your QK transpose. Of course, we are doing this over the non-batch dimensions, hence the -2 and -1. And we normalize by the square root of the embedding dimension. So this is from the original Transformers SDPA implementation or paper. From there, from the attention scores, you simply get probabilities through the softmax operator. And then you just do a weighted sum with respect to all of the embeddings. So very, very straightforward. The only complexity here is the multi-head part. So the core idea here is that you can do things, you can implement multi-head attention by just very cleverly breaking up your final embedding dimension, which is exactly what we do here. So after we do a kind of right when we calculate the forward on the queries, we just simply split up into number of dimensions, number of heads, and then the per head dimension. And so this is, of course, just the full embedding dimension divided by the number of heads. And then the other thing to pay attention to, you just have to be very smart about the specific dimensions that you are using. So very, very straightforward. You calculate your QKB pairs, you break it up into number of heads, you run scale dot product attention. And yeah, that's about it. You reshape and then you apply the final transformation, the output transformation to get back into your original embedding dimensions. Very, very straightforward on the multi-head attention. Even more straightforward is the MLP. So this is just a very, very classical MLP. You have two feed or essentially two matrices, and your activation function here is ReLU. Yep. So you just apply one matrix multiplication, apply ReLU, apply a second matrix multiplication. From there, we go to putting everything together to get a single layer. So a single layer essentially consists of a couple of normalizations, a feed forward and a self-attention. So how do we do this? Well, first we calculate the self-attention, and you'll notice that this is just attention, but where all your inputs for QKB are exactly the same. We calculate the norm, we calculate the feed forward, and then we calculate the norm again. And honestly, the positioning of the norms here are not super important. So here we have post norm. You could have also applied it beforehand. So you could have applied norm 1 to X before this and shifted the norms up by 1. It doesn't really matter too much about this scale. And yeah, I mean, that's about it. Now you have your transformer encoder, which is in a series applies encoder layers. So we can skip these two. These are essentially just creating patches out of images. So we get our input, we add our positional embeddings to them. We go through every single encoder layer and kind of recursively apply the layers. We apply our final post norm. And here is we just pull some embeddings so that we can calculate our prediction of whether or not this is a cab or a dog. So here we have a number of classes substitute. So this is about it. The core implementation is, as you can see, is less than 100 lines of code probably. And this is the consistent way that transformers have been used. So for llama, you do very basic things like replace the layer norms with RMS norm. You get slightly more complicated feed forward function, but the majority of the code stays exactly the same. Before we move forward from here, were there any questions that I can help answer about this implementation? Yeah, I guess, yeah, rushing through this just so we can get into the lectures. Let's finish up yesterday's lectures and then we'll jump into multimodal things.
There's a question online. Why do we need both view and transpose? We could just apply view to change the shape.
Yeah, this is the weirdness, I think, a little bit in PyTorch. And there's view, there's transpose, there's reshape. To be honest, there's not that big of a difference. I think both view and transpose are what's it called? They're like a meta operation, so it's actually essentially zero cost. So the underlying, you don't actually do anything on the underlying tensor. I think the reshape is the one operation that does change the underlying tensor. Yeah, you can manipulate, you can transpose in many different ways. One, I think this is where we ended up yesterday, right? Okay. Okay, so at the end of yesterday's lectures, we were talking about that, pre-training specifically is a highly predictive, it's a highly predictive process, right? And the better that you are at pre-training, the more multiple of orders of magnitude out you can kind of predict where your pre-training will end. So specifically when we talk about kind of OpenAI scaling laws, you can see that they can predict anywhere from 100 to 1,000 net cells. So very, very impressive. But in general, pre-training has taken a little bit of a backseat when we start talking about modern stages of training. So kind of the course structure that we see of training right now is essentially you have three separations, three like very explicit separations, and then there's even more specific separations within these stages. But you'll likely hear people talking about, there's a pre-training stage, there's a mid-training stage, and then there's a post-training stage. And a lot of the work right now is going on within post-training, and within post-training, you'll hear people talk about like instruction tuning or supervised fine-tuning, reinforcement learning, preference optimization. So it's very granular at this point, but on a high level, pre-training is, exactly what we talked about initially. It's the largest scale of unsupervised learning. And you try to do this on a very high quality, diverse text corpora that's in the, tens of trillions of token scale. Mid-training is something that's relatively new. It kind of popped up last year or so, which is that, after you're doing a large scale kind of pre-training, what you want to do is you want to start slowly tuning your data mixtures to be more aligned with kind of what your end goal is. So you can think of this as having very weakly supervised data that's still around like the 1 trillion, 2 trillion token scale. So this might be, increasing the amount of code data that you have in the last 20% of your pre-training, which is becoming a very standard technique to do. Or, for example, mixing in some synthetic instruction following data from other models. So usually this takes up between 10 to 20% of the total kind of total likelihood training. So pre plus mid. Mid is about mid is about 10 to 20% training. And this is one of the really core ways that you can get like a very, very good code model, for example. So you'll do like 30 trillion tokens of, essentially the whole internet. And then the last 20% you'll train on essentially, I guess, all of GitHub, which is maybe 5 trillion tokens. Okay. So after you do this, this is where you get into the post training. And then one core hypothesis that we generally have is that you're not going to unlock any new type of knowledge within the post training stage. And I think this has been there's been pushback against this, but the idea is that you want to build a very nice interface to all of the knowledge that the model has picked up in these like massive stages of training. Model actually follow instructions. And then in reinforcement learning, there's preference optimization, which is can you kind of like slightly tune the model to generate outputs that are more aligned with what humans want to see. And then the recent kind of hot thing is reasoning, which is can you use reinforcement learning, kind of logical or mathematical reasoning. So these are kind of the core stages. And the truth is, one second. I switched to the next slide. Okay. So in general, if you kind of read modern papers, the course stages get very, very granular. So probably the simplest one was the Instruct GPT paper that came out around the GPT-3. You do some preference optimization and you call it a day. That's your aligned model. And then we slowly saw more and more complicated kind of pipelines being developed. So we saw that Llama started having more complex forms of preference optimization, both SFT based and RL based. Tulu, which is from OpenAI, they have like multiple stages now of on policy and off policy RL optimization. And then the recent Quant 3 papers get like very crazy with it, where they have like 4 core stages. Within each stage, you have kind of additional stages. So I don't know if you can read this, but they do everything from like general training to like specifically reasoning, mid training to long context extrapolation, so code distillation. So what we're seeing is that kind of the core recipes that were developed a couple of years ago, that were very simplistic in nature, are now all of a sudden becoming relatively complicated. And by the way, part of this is also organizational. So if you want to have a relatively large team that is building these models, it's very nice to be able to say like, hey, you're doing stage 1 of mid training, rather than trying to get everyone to build a kind of a unified system. Kind of the intuitions of each stage. So pre-training, you can think of as building the foundation. So this is where you learn very general language understanding. You obtain world knowledge, a very large scale, right? We're talking 15 trillion plus tokens, as diverse data as you can get. I mean, an example is like Anthropic. They wanted to get even more data. So they went and they bought a scanning press, and they bought like 2 million books that they were hand scanning to get additional tokens. So this is kind of the level of diversity that you're looking for. And the objective tends to be almost always just very direct next token prediction. And this is essentially, up until very recently, was the very, very expensive portion of training these models. So I think when Quen was reporting, or when any of the open source frontier model report, you'll see usually $40-50 million cost on the pre-training, during the pre-training stage. Post-training alignment, again, is split up usually into 2 sections. So there's supervised fine-tuning, which is, can we get our models to follow instructions well? This is very, very cheap. So I think the DeepSeek models spend, maybe $100K or $200K on this stage, and reinforcement learning around preference optimization is the standard now. So can you figure out how I can write better such that humans like how I write? And the most recent innovation surface area is this RL from verifiable rewards. So this is essentially, we're out of very interesting data and now we have to work with very complex environments. So can we essentially build environments where the verification is, very, very obvious, right? So very obvious here is like, can I write some code that passed all my tests, right? If you pass all my tests, the reward is 1. If you don't pass all the tests, the reward is 0. Or in math, did I just get the right answer at the very end, right? So this is a very easy verifiable reward. And this was likely the biggest breakthrough that we've had so far this year. So if you've ever heard of GRPO, which was DeepSeek's breakthrough, it's essentially that you can do RL towards rewards that are very, very simple to compute. So this is high level where we're at with kind of the core training stages of modern language models. Okay. Before we move on to this, any questions, at least at a very coarse or high level, about why we need all of these individual stages? Cool. Nothing online. Awesome. Okay. Oh, there's.
There is a protocol for this, guys.
So you mentioned that on pre-training, the data should be very diverse and very big volume of data. So how much, like, why the diversity or contribute to the final result of the model? Like, what if we will take only code, let's say, or another very big volume of code, let's say, and try to train it only on code? Does then the model became will have the same cognitive ability to code? Like, I am asking, like, is it essential to have very diverse to then have a model that could, let's say, code?
Yeah, this is a pretty good question. I mean, if you remember the very original code models, like the very original codex that came from OpenAI, their training was essentially from scratch just on code. And I think the realization that came is that you can actually be better at code if you, for example, train on, I don't know, like all scientific documents, right? Or all like math papers, right? Or Reddit threads where people discuss, maybe discuss code or discuss math. So I think what we saw is that in general, you see a unified lift from training on more and more diverse data. And then really what you want to do is if you want to have a good code model, you just continue mid-training on code data. And if you go and you look at like the public papers, so like DeepSeek or Quinn, you'll see that they do exactly this. So in their mid-training stages, the last 20%, they throw in massive amounts of code data, math data, and then synthetic reasoning traces from other models. So yeah, it's not a super satisfying answer, but it seems to be that there's unified lift from training on more than just your target domain.
Okay, can I ask a follow-up question? So you talked about SFT and then doing any type of an RL for further exploration. And with recent thinking models, it feels more like a shamanism rather than actual science as to know when to end SFT, what to start RL on, how to actually unroll the RL. And many companies have different recipes of this. Many of those work, many of those don't, given a situation. And it feels like it's fairly empirical. That's why I use the word shamanism, alchemy, rather than an actual way to essentially increase the scores of the model, like the potential of the model. What do you think about that? Is there any more fine-grained, rigorous way to do it, or we just should hope that God is happy with this SFT checkpoint and we can RLHF on RL on site?
I mean, I mean, let me preface by saying like all of this is alchemy. There's no real math or theory behind any of this. Um, I think there's just different philosophies that people have, right? So if you're OpenAI and you spent $500 million collecting SFT pairs, you probably want to train on that, right? At the same time, DeepSeek didn't have that amount of money, so they put in more work on trying to figure out how to get RL to work because it seems like RL is more sample efficient than doing this type of very large scale instruction following. Um, that being said, the recipes are kind of unified that you probably want to have like a likelihood pre-training phase, a likelihood mid-training phase. You want to do very light instruction following plus preference optimization, and then have kind of a reasoning RL stage. Again, this is very, very coarse. And so, for example, if you saw like, XAI's like Grok 4 release, right? Their argument was, okay, we actually are going to spend 50% of our compute doing RL, right? So the sequencing I think is good and it's consistent across all companies, but the amount of money you place into each stage, I think this is dependent on your underlying philosophy.
Other questions, guys? Any questions online? Okay, I think we can one.
Sounds good. Okay, so let's jump into multimodal pre-training again, primarily starting from kind of the motivation that I shared yesterday, which is we are functionally running out of text, and one of the ways that you can break this kind of barrier is by starting to think about training on very multimodal data. And so we are at that point where if you are a large company, you have essentially surpassed all text-only tokens. And there are now open source models that have been trained on essentially the whole internet. So we need to, if we care about pre-training, we need to start thinking about how can we increase the scope of our tokens. So I think first place we should probably start off with is thinking about, okay, how can we get good image representation? So if you remember kind of when we did the historical walkthrough yesterday, the very first thing that people started focusing on is how can we get good language representations, whether it was, initially starting from words and then moving up to sentences with BERT. How should we think about getting good image representations? And so the motivation here is that, if we can learn some very nice semantic mapping from raw data, which is essentially pixels, we can do a lot of really cool things, right? So we can do things like image classification. We can build out image search if, the embeddings have some type of algebra that you can play around with. We can start thinking about doing image generation because now we can condition on the semantic meaning of kind of these images. So the motivations were very, very clear, right? And people started thinking about this around 2021-ish. And there was a lot of work, but I think the primary line of work that I want to talk about is contrastive methods. And so most of you likely have heard about CLIP, right? So at a very high level, what does CLIP do? So CLIP says, you know what, the way that we're going to learn very good image representations is we're going to try to ground the image representations in text. So what we're going to do is we're going to have two separate models. We're going to have a text model and we're going to have an image model. Again, these are primarily transformers, especially with the recent releases of CLIP. But what we're going to do is we're going to embed, the textual descriptions, captions that you can get from large scale internet scrapes. And we're going to embed the images separately. And then what we're going to do is we're going to try to calculate similarity, again, in a very, very similar way on how we calculate attention similarity, just inner product. And then what we're going to do is we're going to try to maximize the similarity with the correct caption and minimize the similarity with the incorrect captions. And so where do you get the incorrect captions? Well, they argue that you can just take it from the batch. So as you're doing your training, just probabilistically, you're not going to get very similar image within a batch. So you can just treat everything that's not the proper caption as being incorrect. And so this was the core idea of CLIP, right? And the idea is that if you do this very, very large scale training, you should start getting embeddings that are aligned across images and text. And so if you do this, you can start doing image classification, of course, in like a little bit of a hacky way, but you can embed your image and then you can embed a ton of text that's like, you know, a photo of a cat, a photo of a dog, a photo of a giraffe. And then you can just pick the highest similarity. So if you have a very fixed image classification task, you can actually very easily get CLIP to work with you. And from there, it turns out that the semantic embeddings that you get, you can actually start building image search by just building a nearest neighbor index of the images. And you can actually search with text by just embedding the prompt of the text and then looking for the highest similarity objects that you have in this nearest neighbor index. And from CLIP, image generation started becoming relatively popular because now if you have these type of aligned text and image representations, you can start conditioning your image generation model with your encoded prompt, right? And so this was more or less the very big breakthrough that once again came from OpenAI around how can we optimize, how can we learn representations that are unified across both text and across images. But this in itself is still slightly problematic. It turns out that CLIP doesn't scale super well. I mean, if you think about it, as you grow your batch size, you kind of are quadratically growing the size of the inner product that you have to do, and this becomes very computationally expensive. And actually, you do want to have larger and larger batch sizes because you're going to get harder and harder negative samples. I mean, just think about it. You're more likely to get a very similar image if you have a much larger batch size, which means the model now has to distinguish much more granular features rather than just, is there a cat in this image? It should be looking at much more detailed portions of the caption. And so this was the core issue with CLIP and why it was kind of tough to scale the number of negatives that you could have. Okay. And so from there was born this method called SIGLIP, which came out from Google. And so the idea is, again, very, very basic, which is that you just very, very literally replace the softmax loss with the sigmoid loss. So essentially, instead of trying to, increase the score that you get for the correct caption and that simultaneously minimize the score that you get for the incorrect caption, what you do is it's just a binary classification test, which is did I assign the highest score to the correct caption? And so this now allows the model to be trained on kind of individual image text pairs without needing to source negatives from your batch. And it turns out that, from a scalability perspective, this helps a ton. So SIGLIP now you can train with much larger batches, which functionally means you can train with a lot more GPUs. It's computationally very efficient, and we can throw a lot more data on it. So, for example, the original CLIP was trained with 400 million images. I think the SIGLIP variants were now being trained with like multi-billion image caption pairs. And so you can take a look at the visualization and kind of intuitively understand that, yeah, now we go from having this very large quadratic matrix multiplication that we have to do to having a very, very basic, binary classification task. Awesome. And from there, I think people started really, getting very, very hacky with this. They saw that, okay, well, learning off of just captions turns out to not be enough because, if you do a web scale kind of crawl, the captions are usually very, very bad because people don't spend the time to like write the alt text of an image super well. So for things where you need very fine-grained detail like localization, so essentially like trying to segment out a part of an image, the CLIP models were very, very bad. And the very first SIGLIP models were very, very bad as well. So the SIGLIP team now started just adding kind of random components to try to solve this problem. So they started adding like localization aware captioners. So now they ask the model to actually generate out the caption. Turns out it helps a little bit. They started adding a ton of new self-supervised losses that we're not really going to get into. But the core idea was that if you want to fix your image representations, now you have to get very, very hacky, because these very simple type of losses for aligning text and images kind of just don't work well. And it kind of makes sense too, right? The goal of learning a good image representation is to be able to do useful tasks with it. Trying to align very basic captions is not the end useful task that you want to be able to do very, very well. Before we jump into like post clip and siglip, how we were thinking about introducing vision into LLMs, any questions about like just the base intuition about why siglip and clip became very, very popular?
So I wanted to understand, doesn't softmax give us a freedom for doing a classification task? For example, if we have an image pair which has multi-classes in the same image, so doing like a sigmoid only there will distort the model.
Sorry, are you talking about like during inference, or is this specifically during training?
During training, and after that using those embeddings in the inference, for example, on the LMs.
Yeah, I mean, the way that I would think about this is that siglip kind of simplifies the problem a little bit. It says that, okay, I just want to assign the highest possible probability I can to the right caption. And then if I assign a very high probability to the wrong caption, I'm kind of okay with that. Just for the sake of getting good training efficiency. I think in that sense, doing the proper softmax is more principled, but as we learn, getting things to scale up is the primarily what makes things work. During inference, it doesn't matter too much, right? Because like if you're selecting classes, the only thing you care about is that your function is monotonic, right? Because if you want to get the top 5 predictions, right, you don't care if it's probabilities or some unnormalized score, right? The only thing you want to do is just sort if your function is monotonic. And both softmax and sigmoid are monotonic. So during inference, you would just sort by the top scores and take like the top 5, for example. So during inference, there's not functionally a difference. And so because it scales better and it doesn't harm anything during inference, it kind of became the method that won out when we think about image representation.
Okay, thanks.
So during the clip, you said that big batch size harms the training becomes kind of impossible. But can we just take several random samples for negative samples during this clip training, and then it becomes possible, right?
Yeah. So, I mean. Yeah, I mean the core issues you have just this massive matrix multiplication, right? And I think original clip was like 32K samples. So you can imagine you have 32K multiplied by your whatever the embedding dimension is. It's probably like 1024 or something. And you have to do this humongous matrix multiplication. So to your point, I think there are papers that did this, which is they said, okay, we're gonna do this like we're gonna do this matrix multiplication in like a block diagonal way, right? But this is just like this is more of a efficiency question on how you solve this problem rather than like very fundamentally scaling up again how many, I guess, samples you can fit into one humongous batch. I'm pretty sure there are papers that did this. Yeah, I mean, this concept of using a batch to sample your hard negatives is a very old idea. I mean, I think it comes from like Info NCE, which is like a 2010s information retrieval like idea. I think the really nice thing with Siglip is that finding good hard negatives is a very hard task, and there was a ton of research, and then Siglip kind of said, yeah, you don't need to do that. I think actually, if you look at their ablations with clip, I don't think they were better if you were compute controlled, but you could just throw more compute at it. So I think in principle, the clipped way is probably the right way, but just empirically, it's much easier to do this without any quadratic restrictions.
And did they manually label the negative samples for the C clip, or?
So they just don't use negative examples. You just want to get the highest probability on the correct caption.
So it's now more widely used? C clip?
Yeah, I think most people at this point use Siglip, or I guess Siglip 2 as a core backbone for VLMs.
Okay, thank you.
Yeah, we have two questions online. One is explain contrastive loss equation. And I think when you address that, like the other one is a bit more out there question.
Yeah, so the contrastive loss is so I don't have the equation pulled up, but intuitively what you want to do is you want a very high, it's contrastive because you want a very high score on the correct sample, and then you want to place a very, very low score on all the other negative bad samples that you have in the batch. So the idea here is that with the softmax, really what you want to do is you just want to push up, if you push up the probability of the correct sample to be 1, everything else will naturally be 0. And this is kind of why softmax forces this contrastive loss. Siglip is not contrastive because you don't have this negative pushing down at all. So it's possible that the model will put a very high probability on the right sample, but it can also put very high probabilities on the wrong sample. So in that sense, it's not contrastive.
And the other question is, would you recommend Piol, which is bootstrap your own latent, instead of contrastive pre-training? Also, can Piol work on text?
Yeah, okay. So for image representations, there was a large lineage of work to try to figure out what's the best way to learn image representations. I think for these slides, I primarily talk about contrastive, but for example, there's things like masked vision language models. And there's things like, I don't know, what would you call like Dino, like latent self-supervised learning. The truth is, I think the contrastive methods have won because of their simplicity. The other methods like, Dino or bootstrap your own latents are very complicated to train. Usually you do things like student teacher models. I think that was for Dino. And so the training is very, very complex, and it tends not to actually be better than like Siglip. To your secondary point, would bootstrap your own latents work on text? Because text is discrete, just doing like mass language modeling works very, very well. There are teams that work on this. Like I think like Jan LeCun very famously believes that you should be learning text over latents. But again, there's not any real evidence that shows that this is the best way to do it. If you have any discrete data, I think it's very hard to beat like autoregressive models. Okay, cool. So it's like, 21 or 22, whenever Clip came out. And so a lot of people started thinking about, we have these text-only language models that are fairly strong. And now we want to, make these models see, right? So we have good image representation models. We have good, just pure text language models. How can we kind of connect them together in a very minimal way? So the general architecture for most late fusion models was, okay, let's pick up a vision encoder, and this can be anything, Clip, Siglip, I mean, even the other ones, Dino. I think people have tried everything. And we have a frozen language model, so a pre-trained language model that has seen only text. And then what we're gonna do is we're gonna add these fusion layers, and the fusion layers are essentially the glue that sits between the vision representations and the text representations. And so usually these are very, very lightweight layers that essentially, I mean, they translate between the vision domain and the text domain in such a way that you can get your model for a very, very cheap cost to see. And so the example on the right, I think, was probably the very first open source example of these late fusion models. I think this is from the Lava paper. And so the idea here is that if you have an image, what you do is you pass it through like Siglip, and then your fusion layer is a very, very simple 2-layer MLP. And so this is the only part of the whole process that is trainable. And then you take the output of this MLP and you just pass it to a frozen coin. And so what's pretty kind of surprising here that you can do is that the single 2-layer MLP can create embeddings in such a way that a pure text-only language model can actually work over. And so for your task today, you guys will be essentially building out the this exact model. And you'll see that you can actually get surprisingly pretty far just by learning this very basic translation layer between images and text. Now, what's really interesting here is that this also made the contrastive methods kind of blow up, because the contrastive methods very directly learn alignment between text and images. Whereas if you're doing something that's like a self-supervised latent loss, there's not an inherent alignment with text. And so let's wait until the next slide. Okay. And so when these papers kind of came out, people started trying, kind of like when we talked about the transformer, people were trying literally everything, every activation function, moving norms around everywhere. Like people started doing this with these types of late fusion models, right? So people started thinking about, oh, what if we have much deeper fusion, right? So like parts of the language model can actually look back at the vision patches, right? So the very famous paper from Google was Flamingo that did this. And it was like the most hackiest, messiest architecture that you can think of, where they like had a frozen language model, started introducing very gated cross attention dense layers. But the main idea still kind of stood, which is that very, very surprisingly, a text-only language model could actually, when given the proper language of images, could actually reason over images surprisingly well. And by the way, we'll talk about alternative approaches to this, but there are still like very, very modern VLMs that use these approaches. Like on the bottom left, I think this is the Quen VL 2.5 paper. Again, if you look at this, there's like a million things that are going on, because you kind of have to work around the fact that these are individually trained models. Again, very, very surprising that this works, but it turns out that it works super well. Well, not super well, it works well to some degree. And so why did this become so popular? The truth is that this became primarily popular in the open source, because in the open source, people don't have too much compute. So it allowed you to pick up massive, models that were trained with massive amounts of compute and with very little, training these glue layers to allow you to train actually very, very cool models. The other thing is that it turns out that you can kind of translate the capabilities of the underlying language models. So for example, if your underlying language model was very, very good at few-shot learning, it turns out that you could kind of for free get few-shot learning in the image domain as well. So it was a super cheap recipe. As soon as a new language model dropped, in less than a day, you could get a vision language model built that was actually relatively good. And so it became very, very popular, and actually is still very popular to this day. But kind of the question that the big labs started asking is, again, like historically, through machine learning, kind of anytime we had a breakthrough, the breakthrough was because we consolidated things. So there was this question of, why are we learning these things separately? Why can't we learn these things end to end? Again, imagine you don't really care about how much compute you're spending. Like, why can't you learn this end to end? And so this is kind of the biggest separation that I've seen between kind of open source and closed source, was this ability to train very natively multimodal models. And this is what we'll talk about next, primarily from the work that our team did at Meta, because I think this is the only open source work that is available. But before we jump into this kind of novel way of doing vision language models, any questions that we can answer about late fusion models? You should probably ask questions, because you will be, building this during your practice session today. But yeah, any questions here? Okay, so when we started thinking about this, I think this was in 2023, 2024. The goal was, okay, we want to pick, again, the very simplest method that we can, that actually scales up for multimodal training. And around this time, we didn't want to deal with the very continuous nature of images. So our idea was, you can take an image, you can tokenize this image, and to tokenize this image essentially means you can convert an image into a sequence of discrete numbers. We're not really going to get into how to do this today, but if you want to look it up, you can look up like vector quantized models. The idea is that you can just quantize in the latent space into some discrete variables. And then if you do that, now you have something that's very, very special, which is that you have text tokens that are absolutely discrete, and you actually have image tokens that are now absolutely discrete as well. So really, from the perspective of your transformer, it's just taking in some arbitrary number of tokens in, and it's producing some arbitrary number of tokens out. And so the idea was, like, let's not artificially limit the output space to text. Let's actually just generate everything that we can, including images, including text. And the idea is that you can actually model just full documents. So if you have a web page, just model all the text, all the image. In theory, you can model all the audio, all the video. And what you get from here is you actually get an additional thing, which is you get very arbitrary alignment of text and images. So if you think about Clip, for example, Clip has a very, very strict alignment, right? So Clip says that we're going to align one single image to one single caption. So for example, it doesn't align between an image and a paragraph, for example, or it doesn't align between two images and a caption. So when we started thinking about this, we kind of had to prove that this is, a good way that we can actually scale these models up. So the very first question that we had is, can we find some very satisfiable scaling laws, kind of very similar to the scaling laws that we talked about before, across this very large set of modalities? And the idea was that if we can prove that our scaling laws hold under a lot more compute, we can actually train these models completely end to end. And we can get rid of all of these weird, non-pre-training portions of the pipeline for multimodal models. So the idea would be to, don't initialize from Clip, you don't initialize from some pre-trained language model. You can essentially train everything from scratch end to end. So around this time, I think the year that we were thinking about this, the chinchilla scaling laws dropped that we talked about yesterday. And so we started thinking about, okay, how can we extend these scaling laws to start thinking about multimodal models? And so the question that we said is, okay, let's say that we train the model by concatenating different image and text data sets. Note that this is different from training on an aligned data set. This is just training on a direct image data set and a direct text data set. What could we expect the scaling law to be? specifically, how could we parameterize this to kind of make sense? And so what we said is that we're going to introduce this concept of modality competition. So the idea being is that, okay, if you have two data sets that are, if you have two data sets that are completely independent from each other, if you kind of have the perfect model, you can kind of independently model the two data sets, but you don't have a perfect model. So you additionally have some amount of, competition or some noise that occurs from training different modalities at once. So let's subtract that term from the loss. And inversely, there can be some amount of synergy, right? Which is the inverse of competition. The idea being is that we can get better compression maybe on some text data sets if we properly model, audio data sets or image data sets. And then we maintain the same exact scaling law parameterization as Chinchilla did. So we said, okay, there's going to be some level of competition or synergy. There's going to be some functional approximation errors that we get just because our optimization or our model is not optimal. And there's going to be some issues with the optimization as well. And the main thing that we said is that the issues from the optimization are in some way additive across the different data sets. Again, super arbitrary, but it kind of modeled the data somewhat well, so we stuck with it. And the really cool thing that we could get from this is we can actually like very explicitly say that, if we are reducing the loss beyond just very independently modeling the two modalities, we are actually synergistic. And this was, I think there's some audio. Yeah, and this was at that point was kind of the holy grail for multimodal modeling. The idea being is that if you can actually get better performance by training on multiple modalities at once, that's insanely cool. And we should be able to pre-train much better models. So we came up with, well, we didn't come up with it. If you just move around the variables in this equation, you can very quickly get this frontier that says that, hey, we're going to get this, we're going to actually get some synergy from training on multiple modalities. And so, yeah, I think this was in 2023. We essentially said, you know what, we're going to take all the different modalities that exist. So at that time, we took like speech, we took image text pairs, we took code that we actually considered as a separate modality at that time. And we did kind of an insane amount of very large experiments to try to see if we can figure out, is there at any point where we can get benefits from modeling things together? Because the truth is if there are benefits, then the late fusion approach doesn't necessarily work, right? We can get much better results by modeling everything at once. And so it turns out that for speech and text, that was kind of the best level of synergy that we found. And then we fit these scaling laws and essentially said that, at this certain scale, we will see synergy. And so this was, at that time, was like a 30 billion parameter model trained on 50 billion tokens. We went and we trained this model, and it turns out that we actually did see synergy. So we actually saw better loss on text if we jointly modeled speech. Now, if you really think about this isn't too crazy of a thing. Speech is kind of it's an alternate modality of text, right? So in some ways, you're just training on more text that's just represented in a slightly more abstract way. But the idea all of a sudden was very cool. It means that, if we're able to train on, all of, YouTube audio plus text, we would in theory get a better model than if we just train on just text. I think I saw some questions, so I'll pause there. But yeah, this is pretty fundamental when thinking about it.
The question is, could you explain the modality loss in more detail?
Yeah, so actually the loss is exactly the same loss as modeling text tokens. So the idea, one second. Yeah, the idea being is that if you have discrete tokens, then autoregressive modeling works best, right? So if you're generating left to right a document, you can generate a piece of text, then you can generate an image, generate more text, generate two images in a very arbitrary type of alignment. So that was the other beautiful thing, which was that you can use one loss. And kind of one dogma that we had internally is that we believe that no method that had more than one loss ever worked. I actually think this is still true to this day. I don't think you can give a method that has multiple losses that scales very cleanly. So we also wanted to be able to very directly just model everything through an autoregressive loss.
Just like a very niche technical one, what was Bij in the original equation? I think it has the same meaning, yeah. So like for the competition in optimization process.
Yeah. So again, these are kind of made up formulas. This is a variable that you just fit. So in the original chinchilla paper, this is a variable that you just fit in order to model your scaling laws. I think the interpretation, I mean, the way that you can interpret this is that it's the larger this number is, the more error you naturally have because of your optimization method. So we know for a fact that we don't have optimal optimization methods, right? So we're all training with some stochastic first order method. So essentially this stochastic first order method has some natural error on this data set. And that's kind of what that represents. And then the lowercase beta essentially says how much do we reduce this error if we grow the data set size. So in theory, even if you have kind of a crappy optimization method, if you had infinite amount of data, you should not have any error in the optimization. Again, this doesn't necessarily make sense. Like maybe in the infinite case, you will also have error, but it kind of fits for the chinchilla people. So we just kept it.
Fair. There is a bit of an esoteric question. How do you come up with these new ideas? Is it just experience or it has statistics and linear algebra basis?
Yeah, this was a very top-down decision when we were thinking about this. Top-down was we believe that everything should be done end-to-end, completely end-to-end. We believe that everything should have a single loss. We believe that scale would solve everything. So if you really believe these three things, you would try to figure out how to move away from these late fusion approaches. If you say that you have a single loss, well, just having, we know that autoregressive losses work with text. Let's try to figure out how we can kind of fit modeling images into an autoregressive loss. Oh, and by the way, at that time, DALL-E 1 came out, which was actually autoregressively modeling images. So we kind of borrowed that idea because it seemed to work for OpenAI at that point. So this was a much more top-down than bottom-up way to think.
There is a question. Why is the power of DI in the denominator 1? So like for the competition and optimization, so there is DI plus DJ to the power of the beta IJ. And why is DI 1?
I'm pretty sure this is a typo.
Yeah.
Yeah, there should be an additional power.
Yeah, it should be DI to the power of beta IJ plus DJ plus to the power of beta IJ. Yeah.
Yeah, we did correct it in the paper. I guess this is just the old screenshot. Is any questions in the room?
Hey, over here. So if we just for now ignore the approximation and estimation errors, and so on the left-hand side, we have the loss if we model both data sets jointly with n parameters. On the right is kind of average loss if we model data set separately with n parameters. But shouldn't we like consider a loss of the I data set model like with n1 parameters and loss of the DJ data set model with n2 parameters such that they add up to n, because the loss written for independence when the modalities are independent is a loss of 2n parameters actually rather than n parameters.
Yeah, if I understand this, there's a question of like, why are we not modeling the number of tokens per modality separately? Am I understanding the question right?
So is n the number of tokens or the number of parameters? Or
Oh, sorry, n is the number of parameters.
yeah, so the question is on the left-hand side, the losses for n parameters modeled jointly. On the right-hand side, there are like n parameters for one data set and another n parameters for the other data set. So in totality, there are two n parameters.
Oh, yeah, this is an interesting point. The the I mean, the main thing is that we're averaging the loss across the two different data sets here. So that actually maintains some consistency, right? You're saying if I have a model that is size n that's trained on this data set, I get one loss, and if it's trained on another data set, I get another loss. If I model them independently without any issue, I should have the average loss, assuming that the number of tokens between the two are exactly the same. And you also have to make an assumption that distributionally the loss is very similar, which by the way is slightly it's an incorrect assumption to make, because images, for example, will always have higher compression issues, or you will be able to compress them less than you'll be able to compress text. But it turns out that it wasn't like the scaling law curves fit pretty well, and we were able to get, one order or an order and a half magnitude predictions out. But yeah, this is absolutely not a perfect formula at all. Again, we kind of just we BS a line that fits and is predictive. But yeah, you're right.
Thank you.
There is one more question online. How do you define custom loss functions for each such scenario? Do you need to develop your own custom loss? How to develop intuition on to come with own customized losses? I think what you were saying was don't develop custom losses, essentially.
Yeah, don't. There's like three losses that you should know and care about. There's like likelihood loss, there's I guess diffusion loss, and then there's I would even say like GRPO loss. That's probably the three that matter right now. Yeah, you should definitely not be doing anything with your own custom loss.
Okay. Other questions, guys? I think we can move forward.
Awesome. I think this is actually a pretty good time to take a break.
Yeah,
Before
we're on
we
the
move
time.
on to the next.
Sounds good.
Yeah.
So let's take a quick break, guys, and be here in what's the timing? 15, 20 minutes? 15 to 20 minutes. Yeah.
Yes, there's.
We give a discrete data or discrete something like this.
Yeah.
For regressive loss, see this text, something like this.
Yeah.
What do you mean by that?
If you have discrete, so okay. So the question is,
Is that in discrete or which?
if you have discrete data, the likelihood estimation varies.
Well, same discrete data like here,
bring an example of algorithms in on the video. So by saying this way, we mean the code that I didn't say. The constitution of the way that you formulate this. Right. So if I want to generate images in a raw, if I want to generate like the, I want to generate a continuum from the image. Well, we can actually bring them the specification, right? Like from you can do that. The problem is that the number of classes that you now have for a small image becomes so large. But there is work. There's like pixel Armen that does that, like generates pixel art. Whenever we have discrete data, then it's easy to implement the compose and the exactly. The process is like it. So you generalize anything related to this, any program to put all this stuff with like two blocks. You should almost always use like it. But when we don't have a discrete, so then if you have any, for example, videos, then you use the cube. Using it also like what we said is we don't want to do the cube. What we want to do instead is take convert it to a discrete scenario. Or like the whole PPA, right? It's just another model that they can give you. Some vectors. Some numbers. For image. When? And then we model that. You have a single number or you have like 1024 numbers. I think it will like yeah, but you predict a number. It's just the it's like that. Have some numbers that I mean, I can kind of find so. So these were the first people that. And your general idea is that you need to avoid any kind of losses. It's the one. Yeah. This is the PQ either VAU again. So it takes an image and converts it to column. So when I was flexible, we need to split conditions in my opinion. I mean, I think even video generate model as this. Yeah, the piece and also works in other form of like. There are also form of person working with the just right for rendering. It's a lot of image stuff. So you step them on. VQGA. Yes. Oh. Only got that. No. Yeah, most of the time, it's training technology has more data. Yeah. Then there's just like a 10 key dropout. Yeah, input. So I think there's different strategies for doing dropout these endpoints. That's kind of the measure. There's a paper. So I think a lot of people that do drop out on the effective side. Yeah, the parameter. Oh, I noticed the slight difference between 800 and 8100. It's strange. And what can they do? same. Probably the kernels are not the same. So if you want, you can set the internal.
Right, it's in the.
The kernels are sometimes attention kernels are not. I have Thanks. Again, don't follow out. Follow us. Also quickly thing. Like this is any model that's total. Yeah, I left this out of the list. I would look up like that one part. I need a variation. I need that. Break up the let's say you have some called peptide. One of the find that paths one number. But you have to learn. So there's a component. Okay. All the find the number. Now, let's hold on. That's the concept. Basically, versions. Single pattern. Basically. And I also asked.
Okay. It's just that.
Oh. Oh. Alright. Yes. This.
I changed it. For two thirds and just. There's.
I want the. Okay. Very important. Yes. That's it.
Okay, guys, we're starting again with multimodal pre-training.
Okay, cool. So where do we leave off on? Okay, so the main thing is building up the story a little bit. So we realized that yeah, actually it seems like you could actually get benefits if you kind of train everything together, um, rather than doing this type of late fusion approaches. So I think this is really where we started thinking about like, okay, what does the next generation of multimodal pre-training look like? And so we wanted to be kind of as simple as possible. So we started with just the very basic text-only LLM methods, and we wanted to see if these would generalize to multimodal language models. So things like do all the stages that we talked about transfer, do hyperparameters transfer, do architectures even transfer. So the very first thing we did is this was around the time that DALL-E 1 came out, which is also a token level way to generate out images. We said let's just scale up this very autoregressive training of token level text to image models. So just to remind you, the images we quantize into a series of discrete numbers. So you can think of this as, this is a this is a type of language that is used to describe images. So it is kind of just like text. So we started training these purely autoregressive models in order to validate our scaling laws, specifically for image and for text. And so one of the things that we saw, which was for back then when the state of the art was like stable diffusion, some methods from Google, we saw that just doing the very, very boring thing of just scaling left to right autoregressive models on image tokens seemed to perform better than essentially anything else that was out there. The other thing that we kind of realized very quickly was that the scaling laws actually surprisingly held. So if you look at the figure at the right, the larger the model that we trained, the better the loss was, highly predictably. So we started thinking that, okay, this might actually be a scalable way that we can train multimodal models jointly together. And then the next question was, okay, so well, the pre-training step works, but around this time we had these kind of two stages. One was, pre-training, and another one was instruction tuning. And so it turns out that with very, very little text, you can actually get kind of the full instruction following capabilities that you could get with just text only models. And it turns out that this kind of worked for everything. So this worked for, editing images directly. This worked from like, hey, here's a sketch of an image, generate out the full image. Even things that seem kind of obscure of like, oh, here are all the key points of like a skeleton of a human. Can you generate out this type of pose? And this was on the image generation side, but at the same time, it turned out that the image understanding actually worked surprisingly well too. So we were able to ask it to do things like caption, ask it some visual questions, ask it to reason about things. So around this time, as we saw that folks were building these types of late fusion models, it seemed that we came to a recipe that was scaling much better. Of course, if you had a lot of compute, was scaling a lot better than traditional approaches, and it was very simple. So it was completely end-to-end. I didn't have to use a trainable clip or trainable siglip. I can just initialize everything from scratch and train at once. It's kind of exactly what you want. And so kind of the culmination of this was started in 2024. So we started a relatively large effort to try to see if that essentially can we train a multimodal version of Llama with the recipes that we had. So at that time we curated the largest scale mixed modal training data set that was curated at that time. So it was roughly 10 trillion tokens. We took the Llama 2 data, all of the code data that existed, and then we also just scraped everything. So scraped Common Crawl, scraped video websites, and we trained these massive models at that time. 3K GPUs for a couple of months. And then we essentially very basic supervised fine tuning with some very high quality data. And it actually turns out that we were able to beat out kind of all of at that time, the big multimodal models with significantly less compute. So at that time, we had some knowledge that I think Gemini was like the 7dB model that was trained for 4 months. So we got that from our Google friends. And then from OpenAI, we knew that this was about 120 billion parameter model that was also trained for a very long time. So it seemed like, okay, we're starting to very slowly figure out that these early fusion, very boring, just scale things up, don't patch things together, seems to scale very, very well. So again, kind of proof the core philosophy that really all you need is you need to just get out of the model's way, have it learn if it wants to. One single loss, don't do anything crazy, and just train at massive scale. That seemed to be the recipe that was working for everyone at that time. Any questions about this before we move on to maybe a couple of examples and where we go from here? Okay, the question was how much does it cost to train this model? Well, this was a while ago, and this was on A100s, so it was probably, I don't know. Yeah, I mean, I'm just trying to do quick math. Probably like 20 million, in 20 or 30 million in cost. But to be honest, with H100s and with like a proper setup, you can probably do this with like 1.5 million costs now. So like it's definitely possible if you're a startup that you can finish. Sorry? Oh, USD. What? What? Oh, it's too expensive or not expensive? 1.5 million? Or 20 million? Oh yeah, this is A100 era, right? This is like older generation. By the way, we were like complaining that other teams had more compute than us. I remember at this time. Cool.
Other question, guys? I can't see anyone. Okay, nothing online. We can move on.
Sounds good. So right off the bat, when we started doing this, we kind of very quickly realized that the llama architecture, actually the same exact llama architecture that we talked about yesterday, actually didn't scale to multimodal models at all. And so it turns out that we had some very, very core modeling issues, and we needed to resolve these. And we spent kind of maybe 3 or 4 months trying to figure out why there were these very fundamental instabilities in training multimodal models. We essentially distilled it to 2 problems. And by the way, I still think one of these is like a very core problem with transformers. The very first one is that if you think about softmax as an operation, so softmax is scale invariant, right? So if I take like a vector of numbers and I move it around, I add some very large number to it, softmax will give you the same exact output. And this is actually a highly problematic thing because it doesn't tell the model to try to keep the numbers relatively low. And this is kind of where theory and empirical practice kind of break, because empirically we are working with like floating point precision that have a limited precision range. Mathematically, the models, because of this, don't actually care in what range they operate at. So we needed to figure that out. So that was the kind of the very first problem that we had. And the second problem that we had is that if you're really, really not careful about Swiglu, there's essentially, because you're multiplying kind of 2 unbounded functions together, you can get this type of squared norm growth. And this was also a very, very big problem. So for us, it was very surprising because we thought that, you know, the llama architecture scaled very well, had no instabilities when training only on text, but it turns out that it has severe instabilities when you train with multimodal models. And so from there, we kind of introduced a couple of augmentations to the transformer. So the very first thing that we did is, if you think about where the softmax is in a transformer model, the softmax kind of appears in 2 different places. The very first place it appears in is in the attention. And the second place that it appears in is at the very, very end before you calculate the loss. So we needed 2 separate ways to essentially tell softmax to not just blow up all of the norms. So the very first one is QK norm. This is just literally applying layer norm on the queries and keys. So very, very boring approach. It turns out that this works very well and actually helps a lot of different types of instabilities. So a lot of the actually more recent open frontier models all use QK norm, which is fantastic. And the second one is kind of not worth talking about, but there's this concept of Z loss. This is kind of where we deviated from having 1 loss. But Z loss is essentially when you calculate softmax, there's a partition function. So you ask that partition to be very small, and that works. And the other thing is we wanted to essentially add back post normalization. So we had pre-norm plus post-norm. And it turns out that the vision people already figured this out at least the second point. And this was called the Swin norm. There was a paper called Swin transformer that did exactly this. So it also kind of reminded us that we should probably be reading vision papers as well. But these were the kind of the core tiny architectural changes that we had to make to Llama that actually surprisingly have become relatively normal, especially the QK norm ones now. And this kind of solved all of our issues. At the bottom right is high level, how we represent kind of this autoregressive language model. So we tokenize text, we tokenize images into discrete languages. And then you just look it up into an embedding table and everything's very nice and easy to find. Any questions, any intuition I can help build about why the Llama architecture didn't scale? Yeah. So the question is, what type of tools do we use to debug the instabilities? Yeah. Again, this is also very hand wavy, right? So you roughly know how you want the model to operate, right? So you know, like okay, BF16's effective range goes up to like 600, right? So if you're in like individual norms are above 600, you're probably going to run into instabilities, right? So you can kind of plot out all the, we use the term sensors. So you can have sensors that sense different parts of the model during training. And you can kind of look at these sensors, and try to figure out what type of issues there are. Again, this is very BS. Like the joke that we had is that this is like astrology for machine learning researchers, where you're looking at things and trying to infer things that don't necessarily correlate super well. But there are other things that you can look at. For example, like how often do you have to clip gradient norms, right? So you probably don't want to clip norms that, you don't want to clip norms constantly. Yeah, I mean, there are a lot of recent efforts to try to improve the stability of the model. So like the couple of examples I will give is like, a lot of people started using QK norm. So for example, the recent Quen models all have QK norm, right? Then you have like the Kimi models that said that, QK norm causes inefficiency during training. This is actually true. Just because of kind of the memory patterns of having to do QK norm. So for example, they do something where they clip the query and key values in the optimizer. Google, for example, has an alternative form of doing this where they do soft logic capping. So in the attention, they essentially apply a very wide like sigmoid that caps out the query key values. So everyone has kind of figured out that this is actually a pretty fundamental issue, but we can't figure out how to get rid of softmax. So we have these hacky things to try to get it to work. But it is a cool research direction to try to figure out how to like very fundamentally solve this issue. But yeah, so for the sensors that we have, the sensors are usually like gradient norms, weight norms, attention entropy, pre-attention norms, the norm of the partition of the softmax. And then there are more like theoretically grounded optimization things that sometimes you want to track. So for example, you might want to track like what is the largest SVD of your largest singular value of your weight matrix. Again, this is like you're just trying to find things that somewhat correlate with stability. There's no real science behind this.
My question is about that scale invariance problem of softmax, and I wonder about what kind of problem is it that we don't have in simple language models, and that problems come in multimodality.
Yeah, that's a super fascinating question. So, um, I'll make a statement that I think is like I believe in strongly, but I think if you ask other people, they will disagree with this. So, if you have a very, very clean text data set that you're training over, you essentially never need to do any of this QK norm stuff. So QK norm, like these scale invariant in the softmax usually appears when there are parts of your distribution that necessitate having higher norms. So in the multimodal case, we saw that when you model like image tokens specifically, all of the image tokens have a higher norm. Like again, no idea why. The model just decides that this is a good thing to do. We don't know why. The other place that we see this is that if you have data that is very bad, you will have these types of scale invariance issues. For example, you can very easily force instability in a text-only language model if you just take like random like SHA-256 hashes and create massive documents and then include that in your pre-training. Because this is like maximum entropy, right? Like the model will never be able to predict any of this, and this will cause instabilities. So you can like artificially induce it, right? But if you have an architecture that has like QK norm or like soft logic capping, you won't get these instabilities because these norms are just capped off. Like the Llama team took a lot of precautions to clean out all of this really bad data, so they never had a need to do that.
Okay, but for training multimodal models, we already clean that image data, right? We create we did data creation, and right after that, non-clean problem with non-clean data that can still exist, and we have that scale invariance.
Yeah, I think for images, it's more fundamental. Even if you have a very clean image data set, the image tokens will have higher norms. We don't know why. We actually did a ton of experiments. I'm trying to remember. For example, if you have an image only data set, you will still get spikes. Like one idea that we had is that image as a modality requires much sharper attention. So I don't know if you have like a question of like, what is this dog's eye color, right? You probably want to be able to have almost like hard attention on one patch of the image. And so because of this, it seems like the models try to throw out very high norms to get very like hard attention on certain patches. So it seems like a very specifically image video thing. For example, with audio, this is not the case.
Okay, thank you.
So continuing on top of the previous question, could you please again state this scale invariance or maybe define it in a more formal way? How do we get an infinite norm growth? And especially by saying the norm, how do we define the norm for the images? Are we talking about the images itself, like some Frobenius norm, or are we talking about some norm in the latent space, in the queries?
Yeah, I think the formal definition is if you have any vector coming into softmax, if you do vector plus some bias, you will get the same exact output as not adding any bias.
Excuse me, vector plus what?
Some bias term, so just some number, right? So really what softmax cares about is the relative difference between elements, not the absolute. And so when I say norm growth, I'm talking about the pre-softmax norms, right? So it'd be very nice if, for example, you had a softmax, like pre-softmax input that's 111, but 111 and 10,000, 10,000, 10,000 will give you the same exact softmax output, right? So softmax doesn't care about the pre-softmax norms. And this is problematic because then the model, for some reason, when you have images, the model will try to like different elements of the attention will try to out-compete each other by just artificially increasing their norms. And so you see like where's the graph? You can see like the norm graph on the left where you train and the norm graph just completely explodes. Yeah. And actually, I think here it explodes up to 600, which is also, yeah, this BF16 limit of stability.
And this is a universal problem with the softmax, or it's just with the images specifically that you mentioned?
So if you don't have clean text data, this appears to be the case as well. Which is why I think you'll see a lot of the folks that are training like, you know, north of 30 trillion tokens, like you're never going to be able to clean your data set to that clean of a degree. So you see this use of QK norm for models that train like this as well. So it does seem to be a relatively fundamental architectural difference. But I wouldn't say that the scale invariance of softmax is a fundamental issue. I don't think our method of doing QK normalization is the proper way to solve this. I actually don't think anyone has done this properly. Like capping your QK values is super hacky. Like clipping it in your optimizer is very hacky. So there doesn't seem to be. So some folks have tried. So some folks have tried to replace softmax with like a rel u squared, right? I think there's a couple papers that do that. So this also doesn't. It's a lot worse than softmax. So I don't think this seems to be like one of the very core issues that transformers have. That we're just kind of skirting around a proper way to solve this.
Can we extend this further by saying that whenever we are doing some supervised fine tuning, where we usually use softmax, right? It can cause some problems since some threshold, like the volume of the data or the nature of the data, and we are do we have to find some alternatives to the softmax?
No, I mean the thing is that your architecture is defined at the pre-training stage. So if you're fine-tuning, you're stuck with whatever you're fine-tuning. SFT data is also, well, hopefully should be very, very clean. SFT is the stage where you care more about quantity, or you care more about quality than you do about quantity. But I will say it's probably one of the reasons why like the Quen models are like historically have been much easier to fine-tune. Which is why, you know, Quen I think has beaten Llama in usage by like orders of magnitude. So sometimes small things like this matter as well. And then I think especially, I don't know how much of this is true. This is true when we've been trying it, but like especially in the RL stage, RL is relatively unstable as well. So we found models that have like QK norm or soft capping to be much easier to RL, which also is now considered part of the post-training stage.
Thank you.
So when we patchify the image, there will probably be patches that won't hold any valuable information. So my question is that, do we filter the patches, or the attention just handles the non-valuable patches?
I mean, it's very hard to define what a not valuable patch is, right? Because okay, you might say all of the background is not valuable, right? But the question might ask what the color of the background is, right? Interestingly enough, there are methods like run length tokenization of images. So for example, if you have a background that is very similar, you can represent the whole background as one patch, right? These are more efficiency gains rather than core modeling gains. So yeah, I don't think people filter on the patches. I think it's just, again, it's too much of a strong inductive prior to place because you don't know what the right filtering is. Right? It's like it's highly dependent on the context.
So the attention block handles the patches,
Yeah,
like where to put the attention.
yeah. It's a parameterized way to look. So yeah, you just let attention deal with it. But there's, again, for some reason, there seems to be something very fundamental about attention for like vision models that causes it to behave like this. And our best guess is that you need much sharper attention for vision models. And there's some other papers that kind of look at this too. Like there's some stuff like I'm trying to remember the name of the paper, but it's like vision transformers need registers, which it's a slightly different thing, but the argument there is that vision models for some reason always want to place attention on something, even if there's nothing to attend to. So the registers paper argued that, oh, we'll just create, you can imagine like creating an empty patch somewhere that the model can focus on for no reason. So there seems to be something fundamental about vision that we don't fully understand yet. Thanks.
There's this kind of phenomenon for text-based language models, like attention sync. They put many of the attention to the beginning of the sequence when you have text. Do you have like a beginning of sequence token for images too? And if you don't have it, maybe that's the cause of the instability, because when they use models without the beginning of sequence, models get really bad performance. But when they have the beginning of sequence, the model can put much of the unnecessary attention to that. Maybe that's connected to that, or no, I don't know.
Yeah, so all these models have beginning of image because you want to be able to condition on generating an image. That didn't seem to help a ton either. We tried to do everything to maintain the LLaMA architecture, and it just was not possible. At least not on like the surface level, changing the tokenization. Yeah, I'm not sure.
Okay, thank you.
Yeah, I guess I would also say a lot of the modern vision transformers like Swin all have QK, or like they have additional normalization strategies where they place layer norms like everywhere. So it does seem like even the vision folks, not the LLM folks, have discovered this phenomenon as well. Yeah, so I guess this is a couple of examples that we had from our model that were relatively cool around the 4.0 era, which was we were able to essentially generate like full documents with images. So the hope was kind of that GPT 4.0 would take this to a kind of an extreme version, which they slowly are. So now they have the 4.0 model, which is an omni model that is capable of doing both text and image generation. But the idea kind of stands like, it was really cool for us to see that the model can generate like the full Wikipedia page for a bird that you can make up, for example. And yeah, ton of new samples, but the kind of the core thing that we realize is that that we found a relatively scalable strategy for training multimodal models that didn't require us to do this kind of hacky late fusion approaches. And we found that this could actually, again, if you have enough compute to actually do your own pre-training, or honestly, even now you can probably get away with mid-training, you can get much better models than the late fusion ones. So I think that's about it for the multimodal part of this. I think after this one, it's a very likely touch on post-training, and then I think there'll be a much deeper talk on post-training and upcoming. And then we will likely touch upon decoding strategies, just so we can close out the full view of training these models. So I mentioned kind of throughout these slides instruction tuning or SFT, but maybe to just give you guys a little bit more intuition what this is. It's essentially just crazy amount of multitasking in some very structured format. So the idea is that if you can show the model enough, different tasks, it will eventually generalize the tasks that it hasn't seen before. Again, this sounds kind of obvious now, but back when OpenAI was working on this, it was kind of a crazy thing to think that a model would be able to generalize the task that it hasn't seen before. And one of the things that kind of really kicked off the instruction tuning was this concept of there seems to be an alignment problem that we need to fix. So Again, this is kind of a philosophical question, but it seems like these models, they don't fundamentally understand what's good and what's bad. At least at the pre-training stage, they don't. So LLMs may produce, harmful text for language that is not super like aligned with human preferences. In some cases, direct harm. As an example, you likely don't want to be able to get a full step-by-step description on how to make chemical bombs. So in some sense, when people were starting to think about productionizing these models, there was a question of, well, we need to figure out how to solve alignment. We want to be able to produce language models that can align with human preferences and values. And so modern LLMs more or less now do so by SFT and doing direct human preference optimization. But the main concept to kind of pull from here is that essentially there's two axes that you can place every language model at. There's this helpfulness axis, and then there's this harmfulness axis. And the thing is there does seem to be a very direct Pareto kind of frontier here. So in some sense, if you want kind of the most helpful model, you will likely have a very, very harmful model, and vice versa. So it kind of both becomes a philosophical question as well as a research question about, well, what point at that frontier do you want to pick? So, for example, Anthropic is very focused on minimizing harmlessness. It seems like XAI doesn't really care about this. So again, it's a very philosophical question. And probably the thing that became very popular kind of in the big labs for doing this is preference optimization. So the idea here is that you can collect a ton of comparison data that you can actually even take from a production environment. So given a prompt, you sample a couple of outputs. Someone ranks best to worst, and usually these rubrics have many axes that include harmlessness, helpfulness, style, personality. And then what you can do is you can optimize the underlying policy, which is the language model, to try to maximize the reward. And again, the way that you shape the reward is also a very interesting question. And different folks shape it in very different ways. So, for example, if you really, really want to get human alignment, you will get a model that essentially agrees with whatever the human says. And so this was a problem maybe a year ago when people were trying to maximize like the LM Arena score. You probably don't want a model that just agrees with you on everything. So there's now new axes that people try to add into the reward structures. But very active form of research. And so the idea here is that now you have kind of two losses. You have one loss that's next token prediction with the language model. And then you have a new RL loss, which is actually holistic in some sense. We're not going to dive into the equations here, but if you look at the majority of the RL losses, they're sequence level. So the model can actually learn to maximize rewards at a sequence level rather than at a next token prediction level. And this is some intuition about why maybe RL is so sample efficient compared to just doing next token prediction. Any questions here before we move on? This is just super quick. There will be a much deeper discussion.
Okay, maybe you mentioned it, but I want to ask about it. What's the labeler here? Is that response is labeled by human, or is it models, some model?
Yeah, I think this is purposely very vague. I mean, it could be anything, right? If you've ever used ChatGPT where it shows you the two different answers and then you select the best one, that's an automatic label that is. There's also human labelers that are likely placed for like very complex prompts that it's hard to distinguish what's good and what's bad. And there's also, this is relatively new, but this idea of like rubric based scoring. So if you have a model that is very, very good at instruction following, like the Oakring model, you can define a rubric on how you should rank responses. And so you can actually replace human labelers with rubric-based approaches. But this is relatively new, like post Llama 4. But yeah, it's just an arbitrary signal that you can get from anywhere.
Okay, I asked it because there was mentioned a bit upper several models. If we have single model like ChatGPT, we know that humans give some rewards to answers and they collect it. But how is that? How it is done for several models, not one model?
So the question is, how would you use this data to optimize several models?
No, how output of several models are ranked?
How would you rank the output of several models? Specifically for the preference optimization stage or as an evaluation?
In this stage.
Yeah. So usually I don't think you want to do preference optimization where you have different models that are outputting. So there's this concept of in RL optimization of like being off or on policy. So the idea is you want to be on policy as much as you possibly can. On policy essentially means that you are using the most recent models predictions rather than using stale predictions. So if you use other models, you're just going to have very, very stale prediction. So most people don't use other models unless it's the train reward models. If you want to have a very general reward model, but usually, like in the step 2 where you're collecting comparison data, you have a prompt and you just generate a couple of outputs from the same exact model rather than different models.
Thank you.
Can you please elaborate more on this next token prediction versus sequence level, and where does this take place in the pipeline?
Yeah, that's a good question, and I think I think the answer I'm going to give is highly intuition based. So depending on what RL strategy you pick, I mean, most RL strategies, unless you go into things that give you token level rewards, are sequence level based. So for example, if you're doing like direct preference optimization, what you really, really want to care about is that you increase the likelihood of the full sequence, of the correct sequence, of the full correct sequence rather than the wrong one. So the optimization is not on how well you're able to predict the next token, but it's over kind of uniformly over, will this jointly be the kind of maximal probability sequence compared to the previous one? It's kind of super hand wavy, but the idea being is that you can optimize sequences more holistically than you would be able to do if you just did imitation learning with next token prediction.
Thank you.
Okay, we're running out of time, so I think I'll just do one more section. So super, super quick. Last thing to talk about is decoding algorithms. So the main concept is that once you have a language model that models a sequence autoregressively, you need to be able to pick at each token how you're going to sample the next token. So essentially what ends up happening, kind of as you guys know, at every token, you're going to get a probability distribution over all the other tokens. And then essentially there's some algorithm that defines which token you're going to pick. And that algorithm is called the decoding algorithm. So there's some very obvious ones that you can do. So one obvious one is you can just select the token that has the highest probability. You'll note that this will give you the same exact sequence over and over, so you're not actually sampling any types of sequences. The other thing you can do is you can kind of randomly sample from the distribution of tokens. So the idea being is that you just sample from the natural distribution that the model gives you. This is a way that you can get kind of more diverse type of sampling. And then there are more kind of complex strategies that I think surprisingly continue to be used. So one problem that you have if you're just vanilla sampling all the tokens, it's possible that you're gonna accidentally sample a very low probability token if you're generating some very long sequences. And so if you have this like very heavy tail distribution, you don't actually want to sample a very low probability token because it's just gonna throw off the whole generation. And especially when there's like factual knowledge, right? So like, I don't know, the US Constitution was written in that next token there, it's not probabilistic, right? There's like a proper answer for it. And models will actually give probability mass to essentially everything. I mean, it's never going to be zero, it's always going to be non-zero. So there are now methods that are a little bit smarter when it comes to sampling. So one is called top K decoding. So the idea here is very simple. You're going to only sample from the top K tokens in the probability distribution. So idea being is you have a probability distribution, take the top 50 probabilities and then sample, like renormalize the probabilities and then sample from there. Yeah, so essentially this is showing what I'm saying. You can essentially cut off the probability distribution at some size, and then you can increase K, decrease K for more diversity or less diversity. Now there are actually issues with top K decoding because you're not picking K in a very kind of clean way. Top K sampling can either cut off things way too quickly or way too slowly. Again, in the example of like, the US Constitution was written in, your top K should probably be, K equals 1, right? So people were trying to figure out, can we utilize the entropy of the probability distribution in any way in order to get kind of more clever cutoffs? And this is where I think now this is more or less the most common way to do sampling, which is called nucleus sampling, or also top P sampling. So again, like I mentioned, the problem is that our probability distributions are very dynamic. And so when a distribution is very flat, a very limited K is going to remove many options, right? If I say my dog's name is, well, there are many dog names that can possibly exist, right? You don't necessarily want to have a top K that limits only to 10 names, right? And the opposite is true with the example of when there's a very strict fact, right? You actually want that K to be less. So the idea of top P sampling is we're going to pick some cumulative probability mass, and we're going to sample all the tokens from that cumulative probability mass. So essentially what that means is you're going to say, you know what, I'm going to order all my tokens by their probability, and the cutoff is going to be the cutoff that in sum gets the probability up to 0.95 or something like that. And that's a number that you can pick. So essentially you get different cutoffs at different rates, depending on the more or less the entropy of your token distribution. And this surprisingly works very, very well for sampling. And I think this is slowly becoming the standard if you want to get diverse but high quality samples. And I think that's about it for today. So I guess there's a couple minutes left for questions, and then we can have the lunch break. Yeah, I think if you're doing late fusion, you probably just want to just use the raw kind of raw patches that come in, put it through like the VIT that's already pre-trained, have some glue, some connector, and just pass that into the model. The problem with these types of late fusion approaches is that it's very easy to destroy the knowledge that's either in the language model or that's in the VIT encoder, right? Like I'll give you an example. So if you randomly initialize an NLP, right, and then you train kind of end to end your VIT encoder, MLP, and the language model, you're gonna get like garbage gradients into your VIT, right? So you can very easily destroy the VIT, right? So the key thing is like, how can you find a minimal set of parameters that don't touch kind of the backbones that have already been trained a good enough? I think that's the kind of the core problem. And if you look at like like very recent papers, very recent late fusion papers, they like even more increase the number of stages that they have. So they'll do things like, after like with all the stages with text only, they'll do things like, let's first train the MLP connector, and then let's train the MLP connector and the vision encoder. And then let's do very small learning rates, small updates on everything end to end. So now there's like an additional 3 stages that are added. Yeah, it's very fickle. Okay. Just take the direct continuous signal from your cyclic over. Okay. Yes, I will send the slides. What is beam sampling? Yeah, so beam search is that's not used too much anymore. Maybe only used in like translation. So beam search is that well, okay, so you have a probability distribution that's token by token. And if you have an algorithm that only focuses on decoding the current token, you can't optimize for the maximum for the tokens that optimize the probability distribution of the next 5 tokens. So what beam search does is it says, you know what, I'm gonna do a deep search in order to find which 5 tokens maximize my probability distribution. Because it might be that in order to do that, I have to pick a lower probability token on my first try, higher on my second try, lower on my on my third token, and then very high on my fourth token, right? But if you do greedy decoding, you're not going to get that because you're going to pick the highest probability sample now. I think in general, beam search has fallen out of favor. The only place that beam search is used is where you have like a very constrained generation problem. So like beam search is still heavily used in translation. But I think that's maybe literally the only place that I know where it continues to be used. You can get confidence, right? You can just look at the entropy. Like the more uniform the entropy is, the higher the entropy is, the more uniform the probability distribution is. So the less confident the model is. There are some works that look at if you know that you have a strong fact, but you have like a high entropy over nouns, then yeah, you're probably going to hallucinate because you just don't know the answer. I usually tend to be very wary of anything that focuses on probability distribution of tokens. So the only time you have a model that's properly calibrated is during pre-training. So during pre-training, and this is, I think, in a GPT-4 paper, during pre-training, the probability masses that are given by the model are the actual probability or the actual likelihoods of the true token. So, for example, if you have a multiple choice, right, and there's 4 choices, the confidences that the model gives are actually correspondent, like it's calibrated with how good the model is at the prediction. The problem is that once you move away from pre-training, you actually don't want to have calibrated probability distributions. I'll give you an example, right? 2 + 2 = 4, right? If I train on the internet, there's going to be people that write 2 + 2 = 5, 2 + 2 = 3. So if I have a well-calibrated distribution, I actually have to put non-zero mass on 2 + 2 = 3, and I have to place a non-zero mass on 2 + 2 = 5. So if I train on all of the internet, right, there's going to be people that write 2 + 2 = 3. So that sequence exists, right? So I need to put a non-zero probability mask. The moment that you do post-training, actually the whole goal of post-training is essentially to change the probability distribution such that you're overconfident, right? So you'll see usually like if you're doing like SFT, you actually want your loss to increase a little bit. So you're overconfident. That will improve your metrics. And then even worse, what RL does is it says, out of like, if I have for one prompt, I generate 64 generations. What RL does is it says in a greedy decoding scheme, I want to pick the correct generation, right? So it even collapses the probability distribution even further. So that's one of the reasons that it's probably not super useful to have direct probabilities out of a model. And by the way, which is why one of the reasons why most model providers don't give you probabilities. The other reason is they don't want you to distill the model. But, yeah.
Just for your last response, when you say like model could generate or someone could in internet could write 2 + 2 = 5, right? And then on post training, we kind of try to remove this, but we shouldn't remove it completely, right? Because theoretically, maybe I ask something, I don't know, tell me anecdote or some historical summarization, and model should be able to generate text where it says 2 + 2 = 5, but in a like different manner, not in a mathematical manner, but as a metaphor for something, let's say. So could we distinguish that types of like pure mathematic versus like not mathematic situations? Like,
Yeah, I mean, this is just the conditioning on the prompt, right? I'm saying that if you write like 2 + 2 =, you want the model to give you 4 every single time, right? But yeah, like for creative writing, the model can easily distinguish kind of the mode that it's writing in. I mean, the other example is like you want the model to always write like correct code, right? Even though there's code online that is formatted incorrectly or has syntactic issues, right? So the post-training phase is essentially doing in the mode that I want to write correct code, I should drop all probability mass of incorrect code. And that's one way to think about post-training, which is why sometimes people say like the majority of capabilities of a model are kind of built during the pre-training stage. And then the pruning of those capabilities or the selection of the correct kind of generations is done as part of the post-training stage.